And I will conclude my set of 5 lectures on dark matter, and today we will discuss about something different from the previous lectures, and I will discuss about a different candidate, which is the axion. Okay, so the axion is a dark matter candidate that is motivated from particle physics, motivated from other problems in particle physics, exactly as the WIMP was, the candidate I've been discussing in the last lecture. So in this introductory course of only 5 lectures, I will focus on mostly on these 2 motivated candidates because they are both motivated theoretically, but also the target of an intensive research program. So unlike the WIMPs, the axions are very light and also very weakly coupled. So they lead to a complete different physics in the early universe, and also to a very different searches that we can perform here on Earth. And so we can briefly start from the motivation. So I would like to introduce the motivation to the axion, because it will also serve when I describe the axion interactions. And the motivation for the QCD action arises from the so-called strong CP problem. So in order to appreciate the strong CP problem, and I will not give you too many details because there are lots of advanced QFT techniques that you need to know in order to be very quantitative, but just to give you a flavor of what this problem is about. This is the Lagrangian of QCD. You see there is the gluon field strength, the gluon field kinetic term, the quark kinetic term, where the covariant derivative contains the interaction of the quark with the gluons and the other gauge bosons of the standard model. And then there are mass terms for the quarks. Here I'm focusing on low energy, on the low energy theory. Low energy, I mean below the GeV scale, where the only 3 dynamical quarks are the up, the down, and the strange. So this Q is actually an array of 3 quarks. And the mass matrix, I decide to work in a basis where I make it diagonal. I can always choose a basis where the mass is diagonal. So these are mass eigenstates, in other words. So this Lagrangian conserves C, P, and T, which are discrete symmetries, and of course CPT. And here I write of course because there is a theorem ensuring that this combination is conserved for this class of theories. So can we conclude from this slide that we cannot have CP violation or T violation? Because remember, this combination is conserved, so violating CP and T is the same, by strong interactions. So there are 2 additional operators in the Q Lagrangian, in the QCD Lagrangian, that violates the CP symmetry, and these are the 2 operators that are right here. The first one is something new. It's it looks like the gluon kinetic term, but instead of the second gluon field strength, there is the dual, which is the one you build with the tensor epsilon. And there is also another term which is I mean, the previous one is included in this one. It's the quark mass term, where I give an overall phase to the quark mass matrix. Okay, so if you take this e to the I theta q equal to 1, you recover the Lagrangian of the previous case. So it turns out that only one combination of these couplings is physical, and the combination is called theta bar, and this theta bar has an observable consequence, and the observable consequence is the neutron electric dipole moment. So here is a prediction for the neutron electric dipole moment. Electric dipole moments violate CP, of course, so this is CP violating observables. And you see that there is a prefactor which you can compute. There is theta bar. It makes sense that the effect is proportional to theta bar. And then the units that are used to express these dipole moments are the electric charge of the electron in absolute value, so this is a positive number, E, and then centimeter, because electric dipoles have the units of an electric charge times a distance, okay? So now you can compare this theoretical prediction with the observation, and what you find is that this number, this theta bar, which is a combination, it's not just a dimensionless coefficient of Lagrange, it's a combination of different coefficients, has to be less than 10 to the minus 10. Okay, so the strong CP problem boils down to understanding why this combination of dimensionless coefficients of the QCD Lagrangian that can be written there, and they are consistent with Lorentz symmetry, they are consistent with the gauge invariance of the QCD Lagrangian, why this linear combination has to be so small. Of course, one option could be that we just put that by hand, but that's not the satisfactory explanation. We would like to understand the origin of this small number, exactly as we would like to understand the origin of the baryon symmetry. One option could be that the universe started its life with that tiny amount of asymmetry between matter and antimatter, but in some sense you give up your desire to understand the dynamical region, the origin of this number. So here we would like to understand why this number is so small. And a very appealing solution was provided by Pechai and Quinn in the late 70s. And maybe I should stop if there are questions on the strong CP problem, because before I discuss the, the PQ solution.
There is one question, actually, even before the CP problem, is about Anupam is asking how must term become gauge invariant as left-hand and the right-handed quarks?
So, of course, this is the QCD Lagrangian written at low scale. Remember, I told you that I'm considering only the quarks below the GV. So we are way below the electroweak symmetry breaking scale here. So the electroweak symmetry is broken. And the gauge symmetry of this theory is SU3 and U1, where U1 is the U1 of electromagnetic interactions. So since the SU3 and the U1 are vector-like theories, in the sense that left and right fields have the same charge, then Q bar R QL is a gauge invariant combination. So this is the Lagrangian in a phase where electroweak symmetry is broken. Okay.
Okay.
Other questions? Very good.
Don't see any more.
Okay, so let's move on with the Pechai-Quinn solution to the strong CP problem. So here I will also be descriptive because, as you will see, there will be several layers of complicated physics. But let's just say that a general ingredient of this Pechai-Quinn solution to the strong CP problem, or PQ will denote Pechai-Quinn, is the extension of the standard model by adding a new global abelian symmetry, which I will refer to as U1 PQ. So PQ is a U1 symmetry that is a global symmetry. So the transformation angle will not depend on the space-time location, exactly as the baryon number is a global symmetry. Okay, so this is not like the electric charge. Instead, is a gauge symmetry. This is a global symmetry. So the requirement is that this symmetry is a symmetry of the theory, but is broken by the vacuum or spontaneously broken, as we usually say, at some scale f, where this f is much larger than the weak scale, okay? And then the other requirement is that this symmetry is anomalous under strong interactions. So let's discuss about these two requirements separately, and there will be more quantitative. So first of all, here there is a bit of energy scales involved. So there is the GeV scale here, which is the scale of nuclear physics, and there is the weak scale, and then F, so the scale where the Pechai-Quinn symmetry is broken, you have to imagine it much, much larger than the weak scale, okay? So it's a few orders of magnitude above the weak scale. So in particular, the physics involved in the Pechai-Quinn sector is a physics that is a very high scale, at a scale that is not reachable by our experiments. We cannot build experiments probing directly the Pechai-Quinn scale. So the question to us is, do we have any low energy degrees of freedom? And the question is yes. So I gave you in problem one a very simple scalar potential to study, where you can derive explicitly that in the presence of spontaneous breaking of a global symmetry, of a U1 symmetry, so it will correspond to this part of this phase of the theory, okay? The potential I gave you in the exercise will be like this, where the vacuum state, there is, of course, not just one, but they are degenerate. All the circle here corresponds to the minimum energy. And it corresponds to a field value that does not respect the Pecha-Quinn symmetry. In other words, the vacuum state is not invariant once I perform a Pecha-Quinn rotation, unlike the case of the potential here, where the minimum value is for field value 0. So if I rotate 0, it would stay 0. Okay. So we are in the broken symmetry phase. The symmetry is a symmetry of the Lagrangian, but once I solve for the state with the minimum energy, I see that this state does not respect it's not invariant under the Pecha-Quinn symmetry. And you can show in the exercise in problem 1 that there is a so-called Nambu-Goldstone boson in the spectrum. At the level of the exercise, it's just an Nambu-Goldstone boson, which is exactly massless. In the case of the QCD axion, it's a pseudo-Nambu-Goldstone boson, and the reason will be clear. Well, not clear. I will specify the reason in the next slide. And the reason is that the Pecha-Quinn symmetry has another requirement, and the requirement is that this symmetry is anomalous under strong interactions. Okay, so I don't expect all of you to know what an anomaly in quantum field theory is. Let's just say, roughly speaking, okay, this is a very sloppy description, but you can say that the U1 Pecha-Quinn symmetry is a symmetry of the theory as long as you consider only classical transformations. Once you consider quantum effects, you see that this symmetry is actually violated. So it's not an actual symmetry of the Lagrangian because it's violated by quantum effects. So let's not go too deep into the anomalies. Let me just tell you that this axion, this Nambu-Goldstone boson associated with the spontaneously broken symmetry at the scale f, it gets this type of couplings with the gluons, where this is G and this is G dual. G dual is the dual field strength tensor. And so you see that it's not a Goldstone boson anymore. The Goldstone boson only appears through its derivatives in the Lagrangian. Here you have another interaction that you have only if the symmetry is anomalous. And I say anomalous on the strong interactions, which means that this term you induce will be with the gluons. There could be also other anomalies under other gauge groups. I will mention them later. So you could have a coupling with the W's, with the Z's, with the photons, or if you want, you can use the SU2+1 gauge bosons. But the requirement for the Pecha-Quinn mechanism to work is that you generate this coupling to gluons. Then you can generate, and you're likely to generate also something else. Okay. So here, please note that this is really an approximate expression, which I will specify now. So what happens is only above the confinement scale. As you go below the confinement, can you hear me?
Yes.
I got a message from Zoom.
Yeah, a certain point. Just skip.
Okay.
Hello?
Yeah,
maybe can you, Francesco, can you repeat that again? I think we lost some of it, some of the work.
What part did you lose?
I think that just the next slide, I think when you go from this anomalous coupling to the next one. Yeah, this part.
Okay. So I didn't say much about this one. So I was going back to this actually because I wanted to complete the discussion on this and say that gluons are dynamical degrees of freedom of strong interactions only above the confinement scale. Okay? We know that QCD confines at a scale approximately of order 1 GeV. And so quark and gluons get bound within hadrons. Okay, hadrons are mesons and baryons, such as the protons, the pions, the kaons. Okay, so once you go to low energy, the QCD confinement will generate a scalar potential for the axion. Okay, so in this expression here, I put a scalar potential, which is just an approximate expression once I consider minimal displacement from the minimum. Okay, so if I put the minimum at value of the axion field equal to 0, and there is a theorem ensuring me that this minimum is CP conserving. So the axion the potential around this minimum will start quadratically if I do a Taylor expansion. Then you can find a more general expression for the potential. But for this discussion, it's just, I mean, this is not the most precise form you can find, but let's just say that you generate, the important point is that you generate a potential which you do not expect for a Goldstone boson. Goldstone boson has no potential, but the anomaly of this symmetry gives you this potential. So the axion field gets a potential, and the axion field will evolve in the early universe, and it will evolve according to the equation of motion consistent with this potential. So as we will describe in a second, the strong CP problem is solved dynamically because the axion field will evolve and it will place itself in the CP conserving minimum. So this is a very elegant solution because it's dynamical, and the QCD dynamics itself, which is the one responsible for generating the axion potential, will also solve the strong CP problem. Okay. So this is a nice figure where you can see that before you account for the anomaly, a Goldstone boson has no potential. The Goldstone boson is the phase of, imagine this phi is a complex field as in the homework, okay? So the Goldstone boson is the phase, and there is no potential, it's flat. But as you include the effect of strong interactions, then you get a potential, which is a periodic function that you can find in this, you can find, for example, in this paper here. So the things you can compute once you have the potential is the axion coupling, you can compute the axion mass, and the axion, sorry, self-interactions in the scalar potential. And then you can also compute the axion interactions with the other field by simply considering the given model you have in mind, okay? So this expression for the axion mass is the axion mass that you get from the potential. This is the value at zero temperature, to be clear, to be precise. You have to consider also the temperature dependence if you want to do a Rayleigh calculation, as I will argue in a second. So this is the value of the axion without thermal correction, but including the effects of QCD. So is the coefficient that appears here, okay? Once you Taylor expand the full axion potential, which is a more complicated function with trigonometrical expressions, once you expand around the minimum, the mass that you find is given by this expression here. So I normalize this expression with an f of 10 to the 12 GeV. So we don't know the value of f. I told you it's much larger than the weak scale. And as you will see, the 10 to the 12 is an interesting number, maybe a range between 10 to the 9 and 10 to the 12. But in other words, you see that even if you take f as low as 10 to the 9, or actually 10 to the 8, I put it here. So this comes from experimental bounds from different sources, observational bounds and experimental bounds. You see that the QCD axion is very light. Okay, remember the WIMP window I gave you. QCD axion is much, much lighter than the WIMPs. So this is a candidate that is completely different from the ones we've been discussing so far. And you also see that consistently with its pseudo-number Goldstone nature, the couplings to standard model particles are suppressed by this large coefficient f. So here I put the coupling to the gluons that must be there for the QCD axion to solve the strong CP problem. But also you also have the coupling to photons and to standard model fermions. These are model dependent, okay? They may be there, they may be suppressed, they may be enhanced. But this coupling here is necessary to solve the strong CP problem, because now let's discuss this. Remember that the theta parameter of the QCD Lagrangian, there were two thetas, but you can always put all of them in the GG dual coefficient. I told you only one linear combination was relevant. So the theta parameter gets promoted to be a dynamical field within this Pecha-Quinn mechanism. And so you see that the ratio A over F is theta with the same normalization. And as I told you, the axion field evolved toward a configuration where the CP symmetry is conserved. And so this is how you solve the strong CP problem. The problematic term in the QCD Lagrangian now is multiplied by a dynamical field that will relax toward very small values, okay? So this is a very different beast with respect to WIMPs. It's very light, it's very weakly coupled. So we expect two things. On one hand, the detection is very challenging, especially yes, to probe this range of F and of masses. But as I mentioned, I think yesterday during the Q&A or even maybe during the lecture, there are lots of new ideas, especially in the last decade. And there is a nice review from 2 years ago where these ideas are summarized. So if you're interested in learning more about axion searches, you can read this review. But also, given the fact that it's very light and very weakly coupled, he has a prominent role in cosmology, as I will discuss in most of this lecture. So the goal of this lecture is to discuss the cosmological production of axions in the early universe, and both the cold component and the hot component. I will quantify what I mean. Before I discuss about the axion role in the early universe, you may wonder, since I will argue eventually that the axion is a good dark matter candidate, we saw in the first lecture that one important requirement was the stability. And I mentioned that he has a coupling with the photons that is model dependent, but it's you have to trust me here, it's difficult to get this coupling to be exactly zero, okay? So because it arises from a combination from two very independent sources, okay? So you may wonder if this coupling is dangerous and if this coupling may compromise the axion stability, okay? So this is what you will check in problem 2 by showing that I gave you also the intermediate steps that you need to fill the gap to get this derivation for the axion lifetime. And you see that for typical values of F, I put F as low as possible, well, as low as possible, compatible with the discussion we will have on the axion in the early universe. But you see that this is much larger than the age of the universe. So this is safe, okay? There is no problem with this decay. Okay, so next topic is cold axion, so axion dark matter, but I think it's something, this is a good place to stop again, in case there are questions.
There is one question by Ankit, and asking, probably referring to when you talked about anomalies, whether by quantum effects you mean at loop level in the amplitude or at the level of discrete harmonic modes.
So I'm not sure what it means by discrete harmonic modes, but I mean, I don't have the desire to how do you say, teach you the anomalies in only one lecture. Okay, this is I'm touching it very marginally. I'm just saying that if you check that the Lagrangian is invariant just by doing a classical transformation, just doing a rotation of the field, you see that discrete quantization of the fields. I mean, you can check if you want. You can phrase the anomaly in different ways. Okay, one way is if you know the path integral formulation. Okay, you can say that when you do this Peccei-Quinn transformation, which is a rotation on the fields of the theory, this rotation does not leave the integration measure invariant. In other words, you have a Jacobian that is different from 1. Okay, so this is what the anomaly means. So it's a symmetry of the Lagrange. If you write down the path integral, you see this because the path integral is the integral over all the field configuration of the e to the I s. Okay, s is the integral of the Lagrangian. The Lagrangian is invariant, but the integration measure is not invariant, okay? So this is one way to put it. Or you can write down the current associated to the classical symmetry, compute the divergence, and then if you compute the divergence of this current at the one loop level, you find that this is non-vanishing, okay? I mean, but I cannot say more than that because I cannot teach anomalies in 5 minutes. I just want to emphasize that it's an important requirement because it's responsible for the coupling between the axion and the gluons. That's why I wanted to mention that. Okay, is there another question?
Yes, there is. Disha asks, like QCD axion, do we have W axion, Z boson axion, meaning electroweak axioms?
Well, I mean, it depends on what you call what. By QCD axion, I mean a pseudo-number Goldstone boson coupled to gluon through the anomalous coupling. It might be also to the W's and the Z bosons, but the coupling to the gluons is necessary to solve the strong CP problem. The coupling to the W and the Z are not required. So I've never heard of electroweak axions. I mean, in the sense that they couple to W and the Z. Okay. I can go on. Okay, so cold axions. So as I said, if you want to know the axion evolution, the axion field evolution in the early universe, you can solve the equation of motion of the axion. So this is the equation of motion that you find. So let's forget about H for a second. This equation is A double dot, the second time derivative of the axion field, is equal to minus the derivative of the scalar potential. So I put everything on the left-hand side here. So that's the Newton law, if you want. Okay, it's F equal ma, where the force here is given by the derivative of the potential. Remember, the potential was 1/2 m squared a squared. I take the derivative, I get m squared a. And of course, I put here the explicit temperature dependence because I told you that the equation I gave you for the axion mass was the mass for the axion at the time where temperature effects can be neglected, in particular today. But as I discussed the cosmological evolution, I need to be careful also about the mass dependence. And this mass dependence, it turns out to be quite important. Now, there is an additional term with respect to the Newton law, and it's the 3h dA dt. So this is, of course, there because the universe is expanding and the axion evolution is happening inside a cosmological background that is expanding with the rate h. And from the point of view of the equation, this is identical to a problem in classical mechanics where you have an harmonic oscillator with a friction term. If you remember, the friction of the friction forces are proportional to the velocity. So the Hubble parameter acts as a friction term in the equation of the motion of the axion. Okay. So Giovanni, are you still online?
Yes.
Because I see your image frozen. Okay, can everybody hear me? I don't know if there is any internet connection problem.
I can hear you.
Okay, perfect.
Since you stopped, I have a question.
Yes, very good, very good.
Anupam asks, axion can get mass correction from large-scale physics, then how it can be light?
From what do you mean by large-scale physics? Physics at the high energy scale?
Yeah, I guess.
No, but yes. They cannot get mass corrections. I mean, because they are Goldstone bosons up to the oh no. They don't get mass proportional to the cutoff. No, they are, with the exception of QCD, they would be massless. Okay, so the only mass, otherwise you don't solve the strong CP problem. You are talking about something new. I'm focusing here on the QCD axion, so the particle that solves the strong CP problem. And for this case, there are no mass term proportional to F, for example. No mass scale, because it's a Goldstone boson. Okay?
Okay.
I hope it's clear. Okay. So the equation of motion can be, of course, solved numerically just by plugging this expression into a calculator. But that's not what we'll do here. I will just discuss two main regimes, and then I will show you in the next slide the result of a numerical solution. So the two regimes are the result of a comparison between Hubble and the mass. And this comparison between the Hubble and the mass, keeping in mind the classical mechanic analogy, is a comparison because between how effective is the friction term with respect to the force term. So imagine an harmonic oscillator with a friction force. You have to know which effect is dominating and is driving the motion of this field. So when the Hubble parameter is larger than the axion mass, and this happens at high temperatures, so at early times, this is the first phase of the axion evolution, then the axion field, we say, is stuck by Hubble friction. Hubble friction is the effect quantified by this term in the equation of motion, so the axion field does not move. Then at some point, the universe gets colder and cooler, so the Hubble parameter decreases, and the axion mass eventually reaches its zero temperature value. At some point, there is a transition between these two regimes, and the force term will dominate. So you will see that the axion undergoes harmonic oscillations, but these harmonic oscillations, of course, are damped because there is still the friction term that acts as a damping force. And the result is that these axion oscillations that are damped have an energy density associated with it that is decreasing with time. It's decreasing because the energy is getting damped. So the axion amplitude is getting reduced by this friction force. But also this axion energy redshifts with the scale factor as a to the minus 3. So the energy density stored in this oscillation decreases with time as a to the minus 3. Okay? So a to the minus 3 is the behavior that you expect from pressurized fluids, in particular for cold dark matter. So the energy density in axion oscillations behave as cold dark matter. So here is a plot from this reference for the numerical solution. So this is the value of the axion field where it's expressed in dimensionless units as A over F. Okay. And this A over F is a dimensionless quantity that enters the coefficient in front of GG dual. So forget about initial conditions for now. We will discuss them in a second. You see that the red line is the amplitude of the axion field. So you see that you have oscillations, the amplitude decreases, and these oscillations are damped precisely in the way that I was describing. And the energy density stored in this oscillation, more or less, there are uncertainties due to now our ignorance about the precise value for the temperature dependent of the axion mass. So this is just an estimate, but you see that the resulting relic density of axion, cold axion, so the energy density stored in cold axion, stored in these axion oscillations, is proportional to the initial value of the axion field in these units squared times this funny power of the Peche quindi constant F, the symmetry breaking scale F. Okay, so you see that for initial conditions of order 1, N and F around 10 to the 11, more or less, you are in the ballpark that you need to reproduce the axion relic density. Okay. So now the next question is, okay, we we know that F is some energy scale, more or less, and it's the scale where Peche-Quinn breaking happens. But what do we put here for the initial field value? And the answer is that it depends. And it depends on the interplay between Peche-Quinn breaking and the inflationary physics. So inflation is this phase where the universe undergoes an exponential, very fast exponential expansion, where the energy density was dominated by the vacuum energy of a field known as the inflaton. Eventually, the inflaton field decays, and you do what we call reheating. You create the thermal bath, the bath that I've been talking about until 2 lectures ago. And so the question is, during this inflationary phase, was the Peche-Quinn symmetry broken or not? And if yes, was it restored afterwards? Afterwards, I mean during the reheating process. So the answer to this question will define two different scenarios for axion cosmology, which I call pre-inflation and post-inflation. So pre-inflation is the case where you have Peccia-Quinn broken during inflation and not restored afterwards. So the initial value of the field is basically a given number that we don't know this number, but it's only a single number, because you have to imagine that at the Peccia-Quinn breaking there were a domain where the axion field had a well-defined value, and then the inflationary physics stretched this domain to a size much larger than the current horizon of the universe. So we live now in a horizon, in a Hubble patch, where the axion field has only one value. And in this scenario, we only have the misalignment. Misalignment is this. Misalignment is precisely this kind of dark matter production. So the energy density stored in the oscillation is called misalignment because the axion field initial value is displaced from the minimum, so it starts to oscillate and slowly approaching the minimum value. On the other hand, if you are in the post-inflationary case, which is the situation where inflation happened, did its job way before Peccia-Quinn phase transition, and then Peccia-Quinn symmetry got broken, then the sensible thing to do is to average over all the possible field value, because the domain of the universe where the Peccia-Quinn field had a given value were very small, and in particular were very smaller than the horizon of the universe today. The horizon of the universe got much larger, and so we have to average over all the possible field value. We take an average. So the good news is that the relative density depends on F only, because remember this equation. If I have to take an average over this theta I square, well, then I do the average. The average is pi square over 3, but this is a result that is valid if you take the harmonic potential. You can go to a more accurate estimate. But anyway, the important thing is that the theta dependent disappears because you do the average. So the resulting relative density depends only on F. So you can use in principle, you can use the observed abundance of axions to infer the value of F just by plugging in the number that you need to reproduce the amount we observe, and also to infer the axion mass, because the axion mass, if you go back to the equation I gave you, was only depending on F, okay? So this is the good news. The bad news is that misalignment is only one contribution to axion dark matter. In this case, there are other contributions known as topological defects. And there is a recent study by Giovanni and collaborators that they quantified the fact that there are large theoretical uncertainties to this contribution. So once you add also these contributions on top of the misalignment, then it's not clear what value of F will give you the right abundance, because there is a large theoretical uncertainty associated to the contribution of these topological defects. So there is a nice plot that I took from this paper here to summarize the situation. Here there is, on the horizontal axis, the Peccia-Quinn breaking scale, FA, what I've been calling F so far. You see the axion mass can be put on a parallel axis because there is a one-to-one correspondence between the two. And then there is the initial misalignment angle, theta 0, which is what I call theta I, okay? And remember that dark matter, depends on this combination here. So this is precisely the slope of this line that you see here. So you see that in the pre-inflation scenario, where you do not have the contribution from topological defects, and when the initial angle has a single value, so you do not take the average, you have to live along this line. So you see that in particular, it's possible to have a value of F much larger than 10 to the 10 to 10 to the 11. You can go all the way to the Planck mass at the price of paying a small initial angle. So you have to come up with some explanation of why the initial misalignment, out of all the possible values of theta, we ended up to live in a Hubble patch where the value of theta is so much smaller than 1. Okay, so this is the price to pay. You can find reasonable or less reasonable arguments to argue why this angle should be small, but in the pre-inflationary case, you have to live on this line, and you can go to large values of f. Okay. When you go to the post-inflationary situation, then there is a band, so there is no dependence on initial angle anymore because you average. But you see that you have a band for f. This is the result of the theoretical uncertainties that I was discussing before. Giovanni, you had a question?
Yeah, I have many, so maybe it's.
But you or the students?
No, the students.
Oh, okay, very good. Okay, so let me comment this slide and then we can move to the question. So this is just a summary to say that a motivated range for f, with caveats, of course. One of the caveats I mentioned is that you could be in the pre-inflationary case, you can have a small misalignment angle, and you end up in a large f region. This is okay, okay? You need to understand why the angle is small, but it's okay. But if you are in the post-inflationary case, or in the pre, and you take an initial misalignment angle of order 1, then this is a sensible range for the scale f that you derive by imposing that you want to reproduce the observed abundance. So now let's take question.
All right, so let's start chronologically. Lorenzo asks, why axion oscillates? Does axion field start decreasing from early universe up to now?
Yes, so the axion oscillates because in the equation of motion there is a harmonic force acting on it, and that's the reason of the oscillation. It's harmonic force. The reason of why the amplitude is decreasing is because there is the Hubble friction, which is effective until today.
Okay. Then Diviendo asks, with such small coupling, it is possible to thermalize the QCD axion in the early universe? If not, then what is the meaning of the temperature of the axion field?
So let me start from the second question. I never mentioned the temperature of the axion fields. When I say that the axion mass was temperature dependent, I meant the temperature of the thermal bath. Okay, so not temperature of the axion. Concerning the first question about thermalization, that's my next topic. So I would just wait. Starting from the next slide, I will address this issue.
All right. If there are no complaints about the answer, I'll go on with the questions. So Sanket asks, what do you mean by symmetry restoration at the level of mass?
So symmetry restoration, I just mean that okay, so let me say that in the case of the axion physics, and as also in the case of problem 1, the potential giving rise to the Goldstone boson for the axion looks like this, okay, the Mexican head shape. However, this is the temperature, this is the potential at zero temperature, or at low enough temperature. But if you consider the universe at much higher temperatures, then you go in a situation which looks like this. This is, by the way, exactly what happens for electroweak interactions. Okay, electroweak symmetry is broken by the Higgs wave, but if you go at early temperature, the Higgs wave was zero because the potential of the Higgs look like this as a consequence of thermal correction. So they are proportional to the temperature. So for high temperature, you restore the symmetry. Now, in the case of the Peche-Quinn case, then what you have is that if after inflation, if physics associated to reheating produces a thermal bath with a temperature above the critical temperature for Peche-Quinn breaking, you end up restoring the potential in this form, and then you go back to have another Peche-Quinn phase transition after inflation, and then you have to take the average of the angle. Okay.
Right. Tessio asks, in the post-inflationary scenario, is it possible to avoid the domain wall problem?
Yes, I mean, the domain wall problem is present in this situation, but there are known solutions. One of them is n = 1. If you know what n is the anomaly coefficient associated to color. There are other solutions where you introduce explicit breaking of the Pei-Check-Quinn symmetry, and these operators in the Lagrangian will be responsible for the decays of these domain walls. So there are solutions that are available, but in general, the domain wall problem is a serious problem of the post-inflationary case.
All right. So, Tess, you also ask n is the so-called domain wall number?
Yes, yes, n is the domain wall number, yes.
Okay.
Yeah, I mean, if you write down the coupling to gluons, there are, I try to present a simplified derivation. There are anomaly coefficients everywhere if you try to be rigorous.
Then Lucas asks whether you can go over again quickly on what you mean by misalignment.
So misalignment, I just mean that the axion field starts its life displaced from the minimum, okay? And this is something that I'm not telling you the why, okay? This theta I, it's just the initial value. And so at early times, the axion field is displaced from the minimum and it stays there because of Hubble friction. As we go to later times, then it starts oscillating, and you see it follows this trajectory, and it slowly approaches the minimum because the amplitude of these oscillations will get smaller and smaller and smaller. So it's called misalignment because this is the result of an initial misalignment between the axion field and the minimum point. And so if you start precisely at the minimum, you will not have oscillation. You would be in an equilibrium point and you will sit there. So this is the result of an initial misalignment between the minimum and the initial field value.
Right. Disha asks why topological effects are not for pre-inflation.
Oh, good question. So I didn't say that. So they are not there because they get inflated away, basically. So the inflation gets rid of them. So their contribution is negligible.
And Sudipta asks what thing decides the pre and post-inflationary era here?
So this comes as a result of a comparison between different energy scales. So you have to compare the characteristic scale of Pei-Check-Quinn breaking, F, with the characteristic scales of inflation. So you have to compare the value of the Pei-Check-Quinn constant, which is F, with the Hubble parameter during inflation. And if F, let's say, roughly speaking, without numerical factors, if F is larger than the value of the Hubble parameter during inflation, then you are in the pre-case, otherwise you're in the post-case. And then there is another requirement about the reheating. You have to make sure that Tmax, the maximum temperature attained during reheating, is not above F if you don't want to restore the Pei-Check-Quinn symmetry. So there is a set of conditions that you have to satisfy, and this is a comparison among different scales.
Then there is a question by Anupam. Not sure. So it says, if axions are Goldstone boson, then it should be oscillate around minimum of the potential, so there should be no change. What makes difference here? Sorry, you say oscillate around flat potential.
So I mean the axions are pseudo-number Goldstone boson, so not just Goldstone boson. So the potential is not flat. In this slide, you see that this is the potential of a true Goldstone boson, but as a result of the anomaly, the axion field actually has a potential. So these fields configuration along the circle are not equivalent. They don't have the same potential energy. Okay, so the axion potential is not flat because of these non-perturbative potentials generated by QCD effects.
All right, that was the last question. So,
very good. Okay, so now we can go and discuss about hot axions. So by hot axions, I mean relativistic axions, and they are a contribution to dark radiation. Okay, so what do I mean by dark radiation? First of all, so there is a way to produce axions besides the misalignment, but you can create axions also from collisions of bath particles. Okay, so these particles B1, B2, and B3 are particles of the thermal bath. These could be electrons, it could be photons, they could be new particles beyond the standard model. But all I care about is that the result of this scattering will contain at least one axion in the final state today. So if you produce these axions, then they are weakly coupled, so they will just free stream until today. They may reach thermal equilibrium in the past, but eventually they will decouple. So they will just free stream until today, and they are very light. Okay, so how do we unveil their presence today? So their presence can be inferred by studying the CMB. So they can manifest as additional neutrino species. This is a historical way of parameterizing the effect of anything that is relativistic at the time of CMB formation. So you see, in the time of CMB formation, there are photons and there are neutrinos in the plasma. And here I say there could be axions as well, but it could be anything that is light. And historically, you parameterize this as N effective, where N effective is like having more than 3 neutrinos. And so the difference between N effective and 3 is called delta N effective, which is the additional amount of neutrino species that you have at the CMB, of equivalent neutrino species. And this depends on the ratio between the density of the axions and the density of the photons. Okay, so here there is a nice plot where they show you the contribution to delta N effective. You can also phrase this as a contribution to delta G star. There are two axes. I will focus on delta N effective because it's the one I just mentioned. And you see, let's focus on the purple line, which is a scalar, like the axion. So this plot tells you that if you have the axion, or any scalar actually, that it thermalizes with the primordial bath, and at some point it decouples, the contribution to delta N effective is given by this line as a function of the decoupling temperature. Okay, so you see characteristic behavior, and this characteristic behavior is that if the decoupling temperature is lower, then the contribution to delta N effective is larger. The reason for this behavior is that G star, the number of degrees of freedom in the plasma, is decreasing with temperature because standard model species are going non-relativistic. So you can look, for example, at the calculation I did for the hot relics, and you see that the abundance had a G star at the decoupling temperature in the denominator. So you can look back at that equation, at that derivation, and you understand why the contribution to the delta N effective, which is a contribution to the density of these particles, is going up as I consider lower temperatures. Okay, so it's interesting to compare this this theoretical prediction with data. So 0.2 is the current sensitivity of the experiments, but in the next stage of CMB surveys, you can get as low as this value here, this band here. So in principle, we could probe this entire situation. And this is the plot for particles that thermalizes. It doesn't have to be the case. Axion may also be produced without reaching thermal equilibrium, but you still have them around today. So this is the, if you want, the case where the effect is maximal, and the best you can hope for when the particles thermalizes. And you see that, by the way, some of these are already excluded, because if you are here, for example, Planck put a bound, which is around 0.2. So what I want to here, I just want to advertise, I will be quick here, then you can ask me questions maybe tonight in the Q&A if you want. I want to leave also some room for the last part on the Xenon one-ton access, and we have 30 minutes left, so I will be fast here, but I just want to show you some examples of things you can do. And if you want to compute the exact amount of thermal axions, axion produced from collisions of particles in a thermal bath, it's important that you perform a careful prediction, because we are going to measure this quantity very precisely in the future. So you have to solve, the way you do this calculation is by solving a Boltzmann equation, which is precisely identical to the one we discussed in the I think in lecture 3. So it's the left-hand side contains the number density of the axion. This is the factor associated to the Hubble expansion. And then there are collision operators accounting for all the possible processes, which could be scattering or decays of the thermal bath that affect the number density. So if you look at the operators that I gave you for axion couplings, you see that you could have scattering with gluons or gauge bosons. So this is some example of a scattering process that can happen in the early universe, producing axions and maybe also reaching thermal equilibrium for the axion. You see, you can scatter with gauge boson, you can scatter with fermions. And I put here UV and IR because I consider the scattering when it happens above the electroweak symmetry breaking scale and below the symmetry breaking scale. You see there is a different temperature dependence with the rate. There is a mass dependence here, so it's enhanced for other fermions. And so you see that this case here is the most promising because it's efficient at low temperature. And this is something that you can argue once you compare the rate with Hubble. So the rate here scales linearly with the temperature. The Hubble scales quadratically. So the lower the temperature is, and the better it is for the ratio gamma over H. Of course, this is valid as long as you have fermions in the plasma. So when the temperature of the plasma drops below the fermion mass, then the rate goes to 0. Okay, so this is, as I said, promising, and the axion coupling to fermions can lead a detectable signal in an effective, as I was pointed out by this paper. And I can show you some plot of a calculation that I'm currently doing with my collaborators, and we are studying the axion production mediated by coupling to some other quarks of the 3rd generation. So these are scattering mediated by top and bottom. So this is a case that was studied well above and well below the electroweak phase transition. Here we are providing a smooth prediction across the QCD phase transition by accounting for the temperature-dependent XVEV. As I was mentioning, the symmetry breaking of the electroweak interactions is something that happens at the characteristic scale. If you go to higher temperature, the electroweak symmetry is restored, okay? And we are also contributing adding new contribution from axion decays, if you have flavor violating couplings. So just to show you an example, you see that if this is the prediction for delta N effective as a function of FA. And for example, look at the black line. You see that if F is around 10 to the 9, the predicted value of N effective is within the reach of a future CMB surveys. And it's interesting that it's also within the reach of future axion helioscopes. And so you can have a complementary observation of this range for axion dark radiation, and also from the axion coming from the sun. The YAXO experiment is detecting axion coming from the sun. And I will talk about axion from the sun in a second. So this region of F2 to the 9 is very interesting because it provides a signal, potential signal in future axion helioscopes like YAXO. It produces a signal in future CMB surveys. And as I argued before, it's also an interesting range for axion dark matter. Then there are the plot for decays as well. I would like to mention also something else that I did on axions recently. And there is the so-called Hubble tension that was mentioned yesterday in the Q&A. And there is a mismatch between two measurements of the Hubble parameter, one performed in the local universe, so performed today, another one performed at the time of CMB formations. And the substantial contribution to delta N effective could be the origin of this mismatch. And in this paper, we show that the contribution to delta N effective from these axions produced thermally from collisions of the thermal bath, in particular axion coupled to leptons, could alleviate the tension in the Hubble constant. So you see that when you discuss about axions, there is also an interesting interplay with other cosmological observables. There is not only, of course, the amount of dark matter. So to summarize, as I said, the QCD axion is motivated hypothetical particles. There are substantial cosmological consequences, and in particular, if you restrict yourself to this range of F, it's a sweet range because you could get axion dark matter both in the pre and in the post inflationary case. In the post, because we don't need to know the initial misalignment angle. In the pre, you take a misalignment angle of order 1, and that's the range of F that you expect, more or less. And in this range, you also have a detectable signal in the amount of dark radiation, which is carried by the axions. So Giovanni, in the last few minutes, I will mention about what's been going on recently, but this is a good point to stop.
All right, yes, there is one question. Dish asks, sometimes I see the coupling of action with fermion as d mu a, f bar gamma mu gamma 5f, and sometimes I see as f bar gamma 5f. Since these two have different Lorentz structures, which one to use? From Goldstone nature, I believe derivative coupling of action should be used, but I often see the other one without derivative.
Okay, very good question. So the answer is that they're both correct, okay, and they are related. You can take, for example, the one with the derivative, okay, the one you get for a Goldstone boson. You can perform a field redefinition on the fermions, and thanks to this field redefinition, you can get rid of the axion derivative coupling at the price of inducing a new coupling, the coupling between the axion and the axial current, no, the iso, yeah, not the axial current, let's say the pseudo-scalar current of the fermions, the one with the gamma 5, okay? Moreover, these field redefinition that you perform could be anomalous, there usually are, and so you also use a coupling to the gauge bosons. But the answer is that there is not a correct coupling to use. They are equivalent, they are related by a field redefinition, it's just a change of coordinates if you want, but you have to be careful when you relate the two, also including the effect of the anomalies.
Yes, maybe can I comment, because maybe I didn't read so the coupling, the pseudo-scalar coupling, you mentioned it's A f bar gamma 5f. While from the field definition, no, that you just mentioned, you get e to the I a over fa times.
Yes. So there is the
5f. And the two are, yeah, they are the same only in processes with only one external axion.
Yes, because
if you have process with more external action, the derivative is the right one.
The right one, yes. Of course, sorry, I meant if you work at the level of 1 over f, then these field redefinitions are, these field redefinitions are just a change of coordinates. If you go to higher order and so you consider processes with more than, you are absolutely correct, yes.
Yeah, also one has to be careful when you treat the action as a classical field, because then you could have automatically more axion legs, right? Okay, then there is one question by Ankit. Do the QCD axion case correspond to DSVZ and KSVZ model shown in GA versus MA plots, that is diagonal bands in such plots?
So it depends on what plot you have in mind, but usually they provide a band. Yeah, I mean, I don't know what plot you have in mind, but usually they show a band, and they include both of these cases. Typical coupling, yes. So if you look at the what?
Yeah, no, I was reading, yeah, typical coupling versus mass plot.
Yeah, for example, if you plot the coupling to photons versus the mass, okay, then the coupling to photons, the QCD band is well, I remember seeing plots with both the DSF and the KSVZ bands, and the bands corresponds to a reasonable range of the couplings, because these couplings to photons, I mean, the coupling to photons is crucial for most of the experiments, not for all of them, but for most of the experiments. So that is a plot where you often see the coupling to photons. And this is a model-dependent coupling, even within the class of models called KSVZ or DFS, then you can have, it depends on the anomaly coefficients associated to photons. But I mean, if you show me a plot, maybe I can tell you, but now I don't have the plot in mind. So yeah, I don't remember what they show.
All right, Tisha. Okay, while Ankit finds the plot, Tisha asks another question. Since axions
Giovanni, I cannot hear you. Hello? Giovanni?
coupling is related to its mass. Oh, sorry. Hello?
Sorry, Giovanni, I could not hear you, but I can read the question. So let me read the question and then I can answer.
Okay. Okay.
Yes, yes. The answer is yes. Topological defects, they have a theoretical uncertainty. So this is an uncertainty on the value of f that you need to reproduce the right density. So I think the answer is yes. Okay. Can I go on?
Yes.
Okay, so in the last few slides, just a few words on what was announced a couple of weeks ago. So axions can be produced in the sun from several processes. Some of them are shown here. And you see that these several processes are also sensitive to different couplings of the axion. But the important thing is that axions couple to standard model particles. And so since they couple to standard model particles, you could have collisions inside the sun producing an axion in the final state. So since the axion is so weakly coupled, then you eventually end up producing an axion that escapes the sun exactly as neutrino escapes the sun. So they get produced with a typical energy around the kV. The kV is the typical temperature at the center of the sun. So the temperature sets the scale for the kinetic energy of the particles involved in the collision, and you get that axions will escape from the sun with an energy around the kV. So if axions exist, and if they have a coupling with standard model particles that are not too suppressed, and this means not too suppressed means that F is not too large, okay? So if F is not too large and the coupling is not too suppressed, then you can imagine to produce this axion with a significant rate. And you can also try to detect these axions here on the Earth, okay? So that's the idea. There are several experiments, and one of them is the xenon one-ton experiment. So what they've been trying to search. So they've been trying to look for these events. So this is an electron inside the xenon atom. And then there is an effect called the axioelectric effect, where an axion from the sun gets absorbed, gets absorbed by the electron inside the xenon nucleus. And then the result is that you have an electron recoil that will hit your detector with a typical energy of keV. Typical energy of keV because this is the energy that was arriving from the axion produced in the sun. Okay, so can we detect it here? I mean, can we detect this class of events? So the breaking news of 2 weeks ago is that maybe we have seen something similar, but I emphasize maybe. Okay, so here I reported the experimental results. So this is the number of events. As a number of events, I mean a number of electronic recoil events as a function of the energy, the recoil energy of the electron itself, in a wide range from 0 to 210. And so these these black points, sorry, are the experimental data. And this red line is the background that the collaboration estimated, and it arises from the source of multiple sources, okay, from the contribution of multiple sources. And so you see that background and data seems to agree pretty well, okay? The red line is on top of pretty much all the points, but you see that at low energy, there seems to be an excess with respect to the background expectation. So here is a zoomed version of this low energy range. And you see that in the range between 1 and 7 keV, so this part of the plot, they observed 285 events, and the background expectation was 232 plus or minus 15. Okay, so you are more or less 3 sigma away, above 3 sigma, more than 3 sigma away from the theoretical expectations for the number of events, electron recoil events, that you expect to see in these energy bins. Okay, so this was published a couple of weeks ago, and it was also announced in a talk 2 weeks ago. But of course, my warning is that this is not a conclusive discovery, okay? Because there are still issues about the understanding of the background, in particular the one from tritium decays, that are still not completely understood, okay? So it's worth keeping an eye on it, but if you attempt to interpret this finding as the evidence for new physics, one possible interpretation is that we are observing in xenon the axioelectric effect. And so actually the collaboration tried to interpret this data by adding on top of the background also a signal of axion coming from the sun, and that is the preferred interpretation from the statistical point of view. Okay, the best fit that you get is the one with solar axions, and these axions are produced in the ways I was describing before, and then they are absorbed in the xenon, as I also discussed. Okay, so this is something that I believe it's interesting and it's worth keeping an eye on it, but it's still not something conclusive. Okay, so since I have 15 minutes, I think I can summarize in the next 5 minutes, and then we can have the last round of questions. Is that okay? Oh, unless
yes.
there are...
There is a, well, there are two, but
okay, so the link maybe we can discuss at the end
later. Yes, and then there is why the curve is flat. Yeah.
What curve? This
it's, yeah, it's a large KV, it go flat.
The background, you mean?
Yeah.
Well, it does not. You see here. I mean, it's the superposition of several effects. So what you are seeing here on next plot, this plot, but this plot is the same. So this plot it goes from 0 to 30, and this goes from 0 to 200. Okay, so you're just seeing the first part of this plot, where
you say the next plot.
The next one is this. But this is the zoomed version of this. So you're just observing one small portion of this plot, but the background is not flat in general. You see that there are multiple sources with a characteristic energy scale. Okay. Okay, so I think I can conclude, and then we can go back to the question about the plot and take more questions. Okay. Okay, so to summarize this set of 5 lectures on dark matter, you can say, and we should say, and we can say with confidence, that 85% of matter composition in the universe is of unknown origin. And this is the 85%, you remember, I also told you that 26.8% of energy density in dark matter is not understood. This is only by taking the portion of the energy budget with baryons and dark matter. So this is 85% of matter in the universe. So I'm not accounting dark energy here. And so I show you this cartoon in the first lecture. On one hand, we have the standard model that we understand pretty well, although there are open questions there. And then we have this black box, which is 5 times denser and 5 times more abundant, if you wish, than this one. We know there is a communication via gravity, but of course, there is a completely unknown set of other interactions that could arise between the two sectors. And then they will be crucial to eventually discover and learn about the properties of these dark matter particles. And I gave you some examples in the lecture of yesterday of what kind of experiments we could perform. So in these lectures, I discussed mostly two candidates. And since this was an introductory lecture on dark matter, I wanted to start from somewhere, and I thought it was a good idea to start from these two candidates, both because of the strong theoretical motivation, but also because they are the subject of a rich experimental program. The experimental program searching for WIMPs is way more mature than the one searching for axion, but at the same time, the axion one is evolving very quickly recently. So they are both very interesting to study in this moment. And as I said, in the case of WIMPs, it's quite tough to accommodate models given the very strong bounds from several searches, especially direct detection. A large region of parameter space has been excluded. On the other hand, oh, here I have a plot. Okay. Yeah, so maybe you see here they say KSVZ in this line. Okay, so but okay, then we can go back to the one you were suggesting. Yeah, so as I said, for the axion, there is a wealth of new ideas that people have put forward, and this is also something very interesting to follow now. Now, this is a figure that I made a while ago, and it's not meant to be exhaustive or to be complete or to be general, to cover all the options. I just put a random of examples of models in the plane where you had dark matter mass and dark matter typical cross-section with us. You see WIMPs are here, axions are here, but there are a lot of other things, okay? And so there is no limit to the creativity of a theorist when you try to come up with a solution to the dark matter problem. Of course, some of these candidates are not as motivated, but you see that the only thing I want to deliver with this plot is the confusion, in the sense that we really have no idea about the dark matter mass. We have no idea about the dark matter interactions, and I focus on two candidates just because this was an introductory course. So this is just the beginning, if you want, the beginning of the discussion on dark matter problem. It's something that I think everybody should know if you want to work on this. But I don't want to deliver the message that there are only these two candidates. Okay, there are many. Some of them are in this figure, but actually there is many more. And this is basically a summary of the research, most of the theoretical research and also the experimental research on dark matter until more or less 10 years ago. Of course, there are exceptions. There have been people working on axion since the 80s, so I don't want to say that nobody else was thinking about other candidates. But it's fair to say that the majority of the community was looking for dark matter under the WIMP lamp post, okay, until and they're still doing that, and it's something good to do, I think. But as the time goes on, and as the bounds on the WIMPs are more stringent, I could see that people are trying to be more open to new ideas and also to develop new experimental strategies. So as I mentioned also in the direct searches part of my lecture yesterday, the neutrino floor is something that we will get to in more or less 5-10 years at most. So there is a natural ending of this program here where you will eventually hit this background. And so at this point, there are two possible options for research on WIMPs. Either the WIMPs will be discovered and they will be great, and maybe we will see evidence for these particles somewhere else, such as the colliders and other experiments. But at the same time, while we go down in this plot, I believe it's good to also move on with new ideas beyond the WIMP paradigm. So I would like to emphasize that I talked to you about two candidates, but there is much more. I mentioned also that as people are going down in this plot, there is also a very interesting effort going down toward the left of this plot. So try to build new experiments to probe lighter masses, okay? So these are just examples, but there is a lot of ideas along this attitude, okay, to just to move on and find new ideas beyond the WIMP. And maybe the next idea on this plot could be yours. Thank you for your attention, and let's have the last round of questions before we conclude.
Thank you, Francesco. So let me start. There is a question by Ankit. Have they, I think they refers to the Xenon 1 tone. Have they tried to fit tritium background?
Yes, they tried to do the tritium background, and they found that the interpretation with the solar axion is preferred, but they don't know the background well. So, I mean, the model they had for the tritium background had a lower statistical significance for the axis with respect to the one of solar axions.
Dish ask, I think referring to this your plot last, why we have no dark matter candidate between 10 to minus 20.
No, we do. So we do. We have everywhere. So I just put random examples here. I just wanted to show you that you can cover a wide range of masses and cross sections, but this is not a complete list. Okay.
Also, he asked, most of the people study simple dark matter model where there is just one. From matter sector, we know it's very complicated. There are atoms, etc. So does considering elementary dark matter versus dark atoms changes anything?
Yes, yes. There are also models where dark matter is made of dark atoms. So something like the hydrogen atoms, so a bound state of a long-range interactions between two new particles. And this is something that has, it could have a dramatic impact on structure formations, for example, because you could dissipate exactly as baryons do in our galaxy. So you would expect the large-scale structures also to look a bit different, especially at small scales. So there are other. I'm thinking about other situations. For example, if you do direct detection and dark matter is made of atoms, maybe you could also start to see or is made by a nucleus, like a bound state of objects. You can start to see the form factor of dark matter as well. So it could have phenomenological consequences. This modification beyond the minimal elementary particle.
More questions?
So somebody asked me about the plot of figure 77. Page or figure 77?
Yeah. Sorry, figure 16 at page 77.
Page 77. Okay. So, yeah, they have lines. Yes, okay. So you see there are 4 in the caption. There are 4. Okay, I'll put. Maybe I can share my screen with the paper, so I can show everybody what I'm talking about. So this is the paper. This is the plot. Okay. Okay, so you see here that there is a caption where there are theoretical benchmarks. Hadronic axion is the KSVZ axion, okay? It's an axion where basically at the cutoff scale, Yeah, okay. So I don't know actually, because I know that the conventional way to define the hadronic axion is to call it the KSVZ, the one with only coupling to gluons. But it's fine. So you can also have coupling to photons. So this is the KSVZ. You can induce coupling to photons as well in the KSVZ if the new fermions, they also carry electric charge. But you see, so this is a situation where the axion couples only to gauge bosons. Okay, there are no coupling to fermions in this hadronic case. And this E over N is the ratio between the anomaly coefficients, the anomaly of the Pei-Chequin symmetry under electromagnetic interactions, E, and the one under QCD, N. So they show ranges for these anomaly coefficients taken to be within a given range, okay? On the other hand, DFS1 and DFS2, they are models, and the DFS is a model where you also have coupling with the fermions in the standard model, and the DFS1 and DFS2, it's something they define in the paper. I don't remember the precise definition, but these are well-defined model, and you see they have a line, okay? This is, it's not a band, it's a line. The yellow band is, for example, the result of the fact that you consider a range of these anomaly coefficients, and so since it's a range, you cannot have a single line, but you have a band in the plot. So I hope I answer. Let me go back to my presentation, but I hope I answered the question.
Yes, so there is a question by Sudipta. What are the more appealing dark matter candidates instead of axion and WIMPs, in your perspective now?
This is a tough question. Some candidate I like very much are the so-called FIMPs. Okay, so they are produced through freezing, and they have a mass above the KV. This is the warm dark matter bound, and the mass that can be as large as you want, in principle. I like these ones because they have a nice they have a nice mechanism to be produced in the early universe, which is called freeze-in, which is in some sense the opposite of freeze-out. In freeze-out, you are in thermal equilibrium and then you escape from thermal equilibrium. In freeze-in, you try to reach thermal equilibrium and you fail. You do not achieve thermal equilibrium. But it's a predictive framework, at least for physics in the early universe. The bad news is that the couplings that you need to produce FIMPs through freeze-in are very small, so it's very difficult to come up with ideas to test these candidates experimentally. So while physics in the early universe works perfectly, unlike the case for WIMPs, the typical cross sections that you get for these particles are very slow. And so you have to be creative and come up with some other way to test them. But these are candidates that I like and I work on. But of course, my opinion is irrelevant. It doesn't mean that they are the right one.
All right, guess 3:31 now, so maybe we can stop for the moment. We have a Q&A later today for more questions. Okay. Thank you, Francesco, for the set of very beautiful lectures. And,
see you later.
See you later.
Bye-bye. Thanks.
Bye-bye.
Thank you, Francesco.